Hello dear student, we have completed our discussion on the chapter Mechanics of Solids. Now we will solve some problems from this chapter. Similarly, for a circular rod, the bending moment m is equal to y into pi into r to the power 4 divided by r. Here small r is the radius of the circular element and r is the radius of curvature. We have also derived an equation for the depression at a distance x from the free end of a cantilever. A cantilever is a structural element which is being held tightly at one end and loaded at another end. The depression at a distance x from the point of contact is given by y is equal to w by yig into Lx square divided by 2 minus x cube by 6. We encounter this equation while we are deriving an expression for the depression at the free end. And the depression at the free end for a rectangular bar is given by 4 into WL cube divided by YBD cube, and that of a circular rod is 4 into WL cube divided by 3y pi r to the power 4. Here W is the weight which is being hanged at the free end. We have also seen non-uniform bending. Non-uniform bending is when we bend a rod by hanging a weight at the middle of the rod, and this can be calculated or considered as two cantilevers being connected together. And we have derived an equation. In case of a circular bar, the depression at the middle delta is given by WL cube divided by 4y BD cube, and for a circular rod it is WL cube divided by 12y pi r to the power 4. Also, in the case of a uniform bending, that is when we load a beam on either side with equal weights at equal distance from the point of contact, then we call it as uniform bending. And in the case of a uniform bending, the height to which the beam is being elevated is calculated in case of rectangular bar as 3 by 4 WP L square divided by YBD cube. Here P is the distance from the knife edge towards the weight hanger and it is equal on both sides. L is the distance of the rod between the knife points. B is the breadth, D is the depth. Similarly, in case of a circular rod, it is WP L square divided by 2y pi r to the power 4. Let's move on to the first question. A steel rod of length 50 cm, width 2 cm and thickness 1 cm is bent into the form of an arc having radius of curvature 2 meter. If the Young's modulus of the material of the rod is 2 into 10 to the power 11 Newton per meter square, calculate the stress and strain at the convex surface of the rod and also the bending moment. A steel rod it has a length of 50 cm, so it will definitely be the length of the neutral surface always, and it has a width of 2 cm. It has a width of 2 cm and it has a thickness of 1 cm. And it is being bent into an arc of a radius 2 meter. The Young's modulus of the material is given and we are asked to calculate the stress and the strain at the convex surface. While deriving an equation for the bending moment, we have seen that a strain at a surface which is Z distant from the neutral surface The strain at the surface, which is Z distance from the neutral surface, is given by strain at Z distance is given by Z. Therefore, strain at the convex surface is the strain at a point on this surface, and this is at a distance half of the thickness. This filament is at a distance half of the thickness from the neutral plane. Therefore, Z in this case is 0.5 centimeter and the radius is 2 meter. So, it is 0.005 meter divided by 2, which is 0.0025, and this is the strain at the convex surface. Now, we have strain at the convex surface, so we can find stress is equal to Young's modulus into strain. And the Young's modulus is given by 2 into 10 to the power 11 into the strain is 0.0025. Therefore, we can find that the stress, the tensile stress, is nothing but 5 into 10 to the power 8, because we have 4 decimal points here. It is 10 to the power 8 Newton per meter square. So, we have found the stress and strain at the convex surface. Moving to the second question, we need to find the bending moment. So, we have an equation for bending moment. What is our equation for bending moment? M is equal to Y into Ig divided by R. Since we have a rectangular rod, we know that Ig is given by B d cube by 12. Therefore, this equation becomes Y into B d cube divided by 12. So, substituting for this equation, we have Y is equal to 2 into 10 to the power 11. We have breadth. Breadth is given by 2 centimeter. So, 2 into 10 to the power negative 2 meter. Depth. Depth is given as 1 centimeter. So, it is 1 into 10 to the power negative 2 the whole cube divided by 12. So, when we solve this equation, we will get this as 166.67 Newton meter. And this is the bending moment experienced by this steel rod. Next question. A cantilever of length 0.5 meter has a depression of 15 millimeter at the free end. Calculate the depression at a distance 0.3 meter from the fixed end. So, here we are given with a cantilever, and the cantilever, the length of the cantilever is given as 0.5 meter, and the depression at the free end, and the depression here, the experienced depression Y is 5 millimeter. Now, we are asked to calculate a depression at a distance 0.3 meter from the fixed end at a distance x. We have an equation for a depression at a distance x given by Y is equal to W by Y Ig into L x squared by 2 minus x cube by 6. And this will give us the depression at a distance x from the fixed end, and Y will give us the depression. But we do not have the values for W, Y or Ig. Instead of that, the question has given us another information, that is depression at the free end. It is said that the depression at the free end delta is 15 millimeter. So we can use equation for delta. Equation for delta is nothing but W L cube divided by 3yig in the case of a cantilever. So we can use this to substitute for the unknowns in the first equation. The easiest way to do that is just to take the ratio of delta by y so that we can cut off the unknowns. So by taking delta by y, that is we can cut off w, y and ig, and the rest of the equation will be L cube divided by 3. That is what is left from delta. And in the case of y cube, we have in denominator L x squared by 2 minus x cube by 6. Now we can rearrange and find an equation for y. Now when we rearrange, y will be equal to 3 delta L x squared by 2 minus x cube by 6 divided by L cube. Now we have values for all the quantities. We have a delta, it is 15 millimeter, convert it into meter. We have a length is 0.5 meter, and the distance x is 0.3 meter. While substituting all these values, and we can calculate the depression at a distance 0.3 meter from the fixed end is 6.48 into 10 to the power negative 3 meter. And you can see this value 10 to the power negative 3 means it will be 0.00648, and it is very much less than 15 millimeter, that is the depression at the free end. Next question. A rigid rod of 1.5 meter long is fixed horizontally at one end and loaded by a mass of 0.1 kg. Calculate the depression at a point distance 1.2 meter from the fixed end. Diameter of the rod is given to be 2 centimeter, and its Young's modulus is also given. So now here we are dealing with a circular rod. So in case of circular rod, similarly in the case of the cantilever, but we have a different equation. So we have a circular rod which is 1.5 meter long, and it is clamped at one end, loaded at the other end. It is given, weight is given, and we are asked to calculate depression at some point, that is 1.2 meter from the fixed end. We can use the same equation. The depression at a point is given by W, the weight, divided by y ig into L x square by 2 minus x cube by 6. A similar equation, but we need to change this from to the particular situation. Here ig changes because we have a circular rod. Ig for a circular rod is nothing but pi into r to the power 4 divided by 4. And also we need to calculate the weight, but what is given is mass, that is 0.1 kg mass is being hanged. So the weight is calculated as mass into g. So it is 0.1 kilogram into g, that is 9.8. and the weight can be calculated from this equation. So we can rewrite the equation. Y is equal to mg divided by y into, instead of ak, let's write pi r to the power 4 by 4, and the equation L x squared by 2 minus x cubed by 6. Let's try to rearrange this equation. I would like to take x squared by 2 from this bracket to outside. So the equation becomes 4 mg y pi r to the power 4 into x squared by 2 into L minus x by 3, and we can cut off some particulars and we can put in values and find y is equal to the given equation. According to the given equation, we can put in all those values and find y is 0.98 into 10 to the power negative 3 meter. Let's move on to the next question. A rectangular cross section of a cantilever has sides of the ratio 1:2. Calculate the ratio of depression under the same load when the smaller side is vertical and the longer side is vertical. So we are given with a rectangular road, and this rectangular road, suppose this is the cross section of the rectangular road, and the case given is here the breadth, say if it is breadth and this is depth, then the depth is 2 times, this side is 2 times of that of this side. So the distance of it is 2x. So it is of the ratio 1:2. So the question is, what will happen in the case if this is x and this is 2x, and I hang a weight in here by clamping this end, and also in the case if this side is being held vertical, that is, this is the 2x side and this is the x side, again I hang the same load by clamping the other end. So this is the question. What happens, or what is the depression when the smaller side is vertical? That is, when this side is vertical, what happens? Let's solve the first question, and that is when the load is in the vertical side. The smaller side is vertical. So when the smaller side is vertical, we have breadth is equal to 2a while the depth is a. So we have an equation for depression at the free end, which is given by 4 into, in the case of a rectangular road, it is 4 into w L cube divided by y b d cube. Therefore, substituting for b and d, we will get depression delta is equal to 4 w L cube by y. These are all constants, and what changes is 1 by b. b here is 2a into d cube is a cube. So 2 into a to the power 4. We can cancel out 2 and the equation becomes 2w L cube divided by y a to the power 4. Similarly, let's calculate for the second case, that is when the longer side is vertical, that is when the beam is kept like this. When the longer side is vertical, the depth is 2a while the breadth is a. So similarly, using the same equation, delta 2 is equal to 4w L cube divided by y into 1 by breadth is a while the depth is 2a, the whole cube. And now it becomes 4w L cube divided by y. Here a into a cube becomes a to the power 4 and 2 cube becomes 8. And the answer will be, we can cut this off to 2, and the answer will be w L cube divided by 2y a to the power 4. So we have answers for delta 1 as well as delta 2. To find a relation, let's take a ratio of delta 1 by delta 2. So by taking delta 1 by delta 2, we have 2w L cube divided by y a to the power 4, that is delta 1, and delta 2 on reversing it will be 2y a to the power 4 divided by w L cube. We can cut off all the variables and delta 1 by delta 2 will become 4. That is, delta 1 is to delta 2 is 4 is to 1. That is, depression in the first case was 4 times than that of the depression at the second case. So we always prefer the beams with a higher depth in case of construction. Let's move on to the next question. The next question is, the end of a given strip cantilever depresses 10 millimeter under a certain load. Calculate the depression under the same load for another cantilever of the same material, but 2 times its length, 2 times its width and 3 times the thickness. So we have 2 beams of the same material, but the second beam has twice the length, twice the width and 3 times the depth than that of the first beam. That is, if L, B and D are the dimensions here, we have 2L, 3D and 2B dimensions for the second beam of the same material. So we are asked to find the depression or the ratio of the depression, say, at the end. So we are given the depression for the first beam, that is when length is L, breadth is B and depth is D. We have equation for the depression, that is W L cube divided by 3y into Ig, and we are calculating for a rectangular beam so that the equation becomes 4w L cube divided by B D cube into y. Now we have another set of equation, that is, say, delta dash for the second beam. Let's calculate for the second beam, and it is given as 4w. Weight is same, but the length has become twice. So 2L the whole cube divided by the breadth has become twice. So it is y into, instead of b, let's write 2b, and depth has become 3 times. So 3d the whole cube, and this is the depression for the second beam. We know the depression for the first beam. So let's take a ratio of these two, that is delta and delta dash, and get rid of all the variables as far as we can, and find a depression for the second beam. So let's do a ratio delta dash divided by delta. So by taking delta dash divided by delta, let's write in this case a delta dash, we have 2 cube which is 8, and 8 into 4, we have 8 into 4 over here, we have 2 here, and the 3 cube will become 27. So let's write the equation. We have 4 into 8 into WL cube divided by, in case of delta dash, y into 2b into 3 cube is 27 into d. Let's cut off the possibilities here, and in case of delta, the delta, by taking the reverse, it is b d cube y divided by 4 w l cube. Now let's try to cut off all those are possible. We can cut off all the variables. We will become delta dash by delta will become nothing but 4 by 27, because we can cut this off and say it is 4 by 27. Therefore, delta dash will be 4 by 27 into delta. But we know the equation for delta, or the value for delta, is given as 10 millimeter. So 10 into 10 to the power negative 3 meter. Therefore, the delta dash is 4 by 27 into 10 into 10 to the power negative 3, and the answer is 1.48 millimeter. So the depression delta dash is 1.48 millimeter. So in the first case it was 10 millimeter, but in the second case it is 1.48 millimeter, which is very less than that of the first case. Moving on to the next question. For a same cross-sectional areas, show that the beam of a square cross-section is stiffer than that of a circular cross-section of the same material when it is used as a cantilever. Show that for a given load, depression are of the ratio 3:pi. Now it is asked that we have two different beams, one having a circular cross section, we have a circular beam, and also we have a rectangular beam or a square beam. We have a square beam and a circular beam, and the area of cross section of both these are same. So in this case, if the area of cross section of both these are same, which one will be the stronger? That is, for which one the depression will be minimum. So we have equation in the case of both a rectangular and circular cross section. So let's write the equation for both. In the case of a rectangular cross section, we have the equation. In case of a rectangular cross section, delta is given by delta of rectangular is 4w L cube divided by b d cube y. Here b and d are same because it's square cross section. So let's consider both as d and write this equation as 4 into W L cube divided by D to the power 4 into Y. Similarly, for a circular cross section, we have the equation 4W L cubed divided by 3Y pi r to the power 4. And we know that from the equation the area of cross section are same, that is pi r square is equal to d square when d is both and r is the radius. This is the relation, pi r square is equal to d square. So let's take the ratio of both these, that is delta r divided by delta c. What will be its ratio? We have 4w L cube divided by d to the power 4y into, taking the reciprocal of c, it is 3y pi r to the power 4 divided by 4w L cube, cancelling out all the similar quantities, and this becomes 3 pi r to the power 4 divided by d to the power 4. So using this equation here, we can rewrite d to the power 4 using d square as 3 pi r to the power 4 into pi r squared the whole squared, which will become 3 pi r to the power 4 divided by pi squared into r to the power 4. On cancelling similar quantities, we will get delta r by delta c is equal to 3 by pi, or delta r is to delta c is equal to 3 is to pi. And this is how we can solve for delta r and delta c. And it will give us a ratio 3 is to pi. We know that value of pi is greater than 3, that is 3.14 etc. So for a beam, in case of a beam, we can say that the depression caused in this quantity will be minimal, that is less than 1. Therefore, depression in the case of a circular beam, delta c is higher than that of delta r. Depression caused by a circular beam is higher than that of the depression caused by a rectangular beam, which in turn means that a rectangular beam is more stiffer than a circular beam of similar cross section. Moving on to the next question. A rectangular bar of 2 cm breadth, 1 cm depth, and 1 cm depth and 100 cm of length is supported at its ends, and the load of 2 kg is applied at the middle point. Calculate the depression at the middle point. Now we are asked to find, and this is the case of a non-uniform bending, when the weight is given at the middle and the bar is supported by 2 knife edges. So we are asked to find the depression at the middle point. We have direct equation to find depression at the middle point. In case of a rectangular bar, it is WL cube divided by 4B D cube into Y. And here the W is weight, but what we are given is the mass. So we have to write, instead of W, it is mass into acceleration due to gravity, L cube divided by 4B D cube into Y. All the other quantities are given. Let's substitute. It is 2 kg into 9.8 into length is given as 100 centimeter. So 10 to the power negative 2 meter. 4 into breadth is given as 2 centimeter. So 2 into 10 to the power negative 2 into the depth is given as 1 centimeter. So 1 into 10 to the power negative 2 meter, the whole cube, into y is given as 200 GPa. So it is gigapascal. 200 gigapascal. 200 gigapascal is 200 into giga is 10 to the power 9. Now Pascal is another unit for Newton per meter square. So we have a direct conversion. So here y is 200 into 10 to the power 9 Newton per meter square. And while substituting and calculating, we will get an answer as 1.225 into 10 to the power negative 3 meter. 1.225 millimeter is what it is being bent down due to this weight. Next question. A beam of width 2 centimeter, thickness 3 centimeter, supported horizontally on two knife edges 80 centimeter apart. And loaded with weights 10 gram on each side, which projects 15 meter beyond the knife edge. 15 centimeter. If the center of the beam is elevated by 2 millimeter, calculate the Young's modulus of material of the beam. Now we need to calculate the elevation. We are given elevation, so we need to calculate the Young's modulus. So we have an equation for elevation. Since it is a rectangular bar, the equation for elevation is given by 3w L square divided by 2yb dq. So we can rewrite mass with mass. It is 3 mg p L squared divided by 2yb d cube. So let's write an equation for y, the Young's modulus. The Young's modulus become 3 by 2 into mg p L squared divided by bd cube into h. We have all values from the question. Let's substitute 3 by 2 into mass. What is the mass? It is 10 grams. So let's convert it into kilogram. 10 to the power negative 3 into p. P is the distance from which it is being hung. So we have to substitute for g, 9.8. Now p is the distance, that is 15 centimeter. 10 to the power negative 2. P is this distance, the distance from the knife edge to where the weight is being hanged, into the length is not the length of the entire rod, it is the length between which the rod is being supported, the distance between the two knife edges, and that is 80 into 10 to the power negative 2 the whole squared divided by the breadth 2 into 10 to the power negative 2 into depth 3 into 10 to the power negative 3 the whole cube into the height, the height to which it is being elevated. It is 2 millimeter. So it is 2 into 10 to the power negative 3. On calculating, we will get it as 13.06 into 10 to the power 9 Newton per meter squared. And this is how we calculate the Young's modulus of a material using the pin and microscope method, which we have discussed in the class. This is what we do in the laboratory. We calculate Young's modulus of a given material. Thank you for watching the video. See you in the next video.